Okay, in this video we're going to kind of finish up talking about equilibrium distance. So I'm going to redraw my graph with R, and I'll have net force and potential energy both on the same graph. And I'll draw the force in black. It's the net force, and it'll look something like that. And it crosses zero at the equilibrium point. I'll call R equilibrium for short. And then I'll draw in the potential energy. So the potential energy is going to look something like that. Okay? With the important point being that the potential energy is the lowest at the equilibrium distance. This is the lowest point. Okay, and we discussed that the potential energy will decrease as they come closer together because the work done on the molecules by the attractive force will decrease their potential energy, but then the work they do against the repulsive force will increase their potential energy. So at this equilibrium position with especially negative potential energy. So I want to think about what will actually happen at this distance. So say I have my two molecules, and they're this R equilibrium distance apart. And let's look at this force graph. So there's actually no net force on them, right? So no net force at this point if they kind of start out there. So let's say we kind of stretch them apart a little bit. Let's try to stretch them apart. So now this is some distance that's greater than R equilibrium. That on our graph is going to move them from here to maybe here. And here again, kind of the things below the x-axis are attractive and things above are repulsive for the force. So that means that we would have a net attractive force. Right? And that's going to bring these guys back together. Or if I could take them from the equilibrium position and make them move in closer, so this distance would be less than our equilibrium, then I would have a repulsive force. Again, so we're going to be moving from here to here. And now you can see that there's a net repulsive force. Repulsive force. And that's going to make them want to stretch back out. And so you see that at this equilibrium distance, they're kind of at rest in a certain way. They're extra stable. Because if we pull them apart, like we did down here, there's going to be a force that brings them back together. And if we push them together, like we did over here, there will be a force that pushes them back apart until they get to the equilibrium distance. And then there will be no net force again. And so you can kind of think about this as two balls connected by a spring. And springs kind of have this, certain distance where they're kind of not stretched out at all. And that's their equilibrium distance. So we can think about this spring as kind of normal. And if we stretch it out, it's going to want to bring the things back in. Until when? Until they're back at their equilibrium position. And if we push them together, they're going to be kind of bunched up and they're going to push it back out. To where? The equilibrium distance. And you see that at this equilibrium distance, the molecules are especially stable. They're really stable. They really resist change. Right? And at this position, they kind of want to stay there in a way. And it also happens to be a place where it has the lowest potential energy. Lowest potential energy. And in fact, these two things are saying the same thing. And that is another way to look at the potential energy. And in the next video, we'll talk about what it means to have negative potential energy and zero potential energy, and kind of work with this a little more. So the take home from this video is that at the equilibrium distance, the net force is zero. It's also associated with the lowest potential energy. At that distance, the two molecules are especially stable. They kind of like staying at that distance. And that is very related to the potential energy. And that's what we'll talk about in the next video.